Hey everyone. I'm going to go over some of the stuff from lab number 4. Recall that I've removed the lab assignment requirement, so you're not required to do these labs, but I thought it would be useful to go over some of these problems so that you have more examples of things relevant to the homework assignments and stuff of that nature to refer to. Also, these lab reviews include sometimes APA style write-up and things like that that should be of help. So in this lab, we had a bunch of different things. I had you explore doing regression with categorical variables, how it can work and how it can fall apart, and then comparing that to what you would get with the Ttest, which is used to compare 2 group means, and an ANOVA, which is used to compare 3 or more group means, technically 2 or more group means, but generally you use the Ttest in that situation. So we'll take a look at those problems, and then we've got some stuff on missing data, and we have some stuff on power. All right, so the first question here asked you to use a Ttest, ANOVA, and regression to compare 2 groups below. We had 2 groups, a group that received information through just a lecture, and a group that received information via computer tutorial or a computer lab. And you can see their scores on a specific exam. I created the data just in R. What you can see is I created basically 10 scores. You can see that with the exam, and then for group F, I've got what group they were in, and then also I created a numeric variable indicating which group they were in, the first or the second group. The reason why I did that is that oftentimes when you import data in R, it will come in numeric with just a handful of different numbers representing the categories. And that can sometimes lead to some challenges in doing these analyses. So first off, I did a Ttest, and you can see the Ttest results here. We can see that, oops, one second, everybody. You can see the Ttest results here. And main thing to take a look at, we get a t-value of 2.39. We get a probability of 0.043 and stuff. Other things that you would typically get here, you can see the group means. The lab mean is 9, the lecture mean is a 7. We'll see how all of those 3 things relate to what we're going to get when we run this with regression. We can see that we can ask for an effect size. The effect size here is Cohen's d. That's the standardized mean difference. One way to think of that is that that's an indication of how different the 2 groups are in terms of the standard deviation. It's a nice measure because it can be used to compare across different research studies using different approaches and different techniques, whereas just comparing people in terms of their raw score differences really doesn't give us that sort of comparability. Look, we do an ANOVA. We get an F value of 5.71. That's actually just our t value, 2.39 squared. And then you can see the probabilities are exactly the same for the two analyses, which they should be because they're doing the same thing in slightly different ways. So it's equivalency there. The eta squared statistic is a common effect size statistic for ANOVA. In this case, it refers to the proportion of variability in exam scores that's explained by which group somebody is in, and it's interpreted as a proportion. So you can see about 42% of the variability in scores is explained based on what group people are in. The next thing I did is I did this in regression. And when we have a dichotomous variable, that is a variable with only 2 categories, we can just drop it right into regression, and we can see what some of the things that we get here. We can derive a regression equation, which we'll use. We can see we have a t-value. The t-value is 2.39 here, probably 0.0438. We can see we get an F value that has similar results, and just comparing that to earlier, we can see that we have exactly the same T and F values produced. Interestingly, you might look at the R square value and the eta squared value. They are also equivalent because they're measuring the same thing. They're just they're measuring how much variability in the outcome is explained by the predictor variable. In this case, the predictor variable being the group and the outcome being the exam score. So that's for, and you can see, you can also run an ANOVA table here. You can see all the sums of squares and everything come out the same. The next thing I asked you to do was add a 3rd group, a group called discussion. where people are just discussing the results, and there's no t-test equivalent here because t-test is only for comparing two groups. When we have three groups, we can use analysis of variance, and that's what I've done here. It gives us an F of 15 and eta squared of 72 and change. Next up, I asked you to do regression incorrectly. This would be using the numeric predictor variable, that 1, 2, or 3 to indicate what group they were in. And the thing we see is we get a t-value that is 1.79. We didn't get a t-value above, but one thing that we can also see is that our r-squared value is nowhere near what it was in the first example, which was around 0.72, I believe. You can see when we run our ANOVA based on that incorrectly set up data, we get an F value of 3 and something, whereas it should be from before these two values, 15.76 and our eta squared of 0.72. Oops, I'm sorry, I seem to have pasted that twice in the file, but the key issue here is we've got the wrong values. All right, a correct regression approach. Here we would be analyzing the data, making sure that our predictor variable was designated as a factor. That is, that R knows that this is a variable that is categorical, not a numeric variable. When we do that, R will automatically dummy code our variables. And what it's doing in this case is it's comparing everything to the discussion group. You can see whatever's left out is what's being compared to the discussion group. We get these two t-values. That's not really particularly useful, but when we look at our ANOVA table, we will get some useful statistics. We see our r-squared is 0.72, exactly what it should be, what we got with the ANOVA. And then our value when we run the ANOVA, that's where we get the F model statistic is 15.76, just like it was when we ran regular old ANOVA. Now, practically you won't be doing much with regression with these sorts of categorical variables on their own, but this is kind of a gateway to stuff that's covered in Lab 5 and homework assignment number 3, where we're dealing with interaction effects, where we're dealing with interactions particularly between continuous variables and categorical variables. And that's when all of this stuff becomes really useful for regression and lets us go way further than we could possibly go just using ANOVA techniques. All right, some multiple imputation stuff I asked you to do. I wanted to go over some of the code here. This is using the Amelia package. You could also use the mice package if you're interested in that. You can see the missing data handout for some nice examples. We use Amelia along with the Zelig package. And the commands for multiple imputation, just this line right here, where you can see my my cursor, MI, that's just where I'm putting the imputed data sets. The command is simply Amelia, the name of the data set that has the missing data, and M equals 20 means give me 20 data, give me 20 multiply imputed data files. Really, really simple to run, really easy command. And you can see it runs for a while. It gives you all of this output. A few things that it gives you, these chain lengths in general, you want those to be relatively small. The longer they are, the harder it took. The longer it took rather, and the harder it was for Amelia to converge and to find a stable missing data solution. It gives you some information about what you would have if you had list-wise deletion. 241 cases had had complete data, so a lot of missing data throughout. Patterns of missingness in the data. I like to look at this because if you only have 1 or 2 patterns of missingness, that may indicate some problem, like a question was left out or something of that nature. If you have a lot of different patterns of missingness, probably less to worry about because it's probably a little bit more of a random pattern. Then you can see fraction missing. This is useful to examine, you want to make sure that you don't have a single variable that is like completely missing or has 95% of the cases missing. So we can see here we've got nothing more than 0.13. Very useful for reporting also when you have multiply imputed data. You'd say something to the effect of missing data ranged from 0 to missing data on items ranged from 0 to 0.134. These loop statements that I've written are there to compute the scale values. This is necessary if you're using scales because you don't want to create the scale value and then try to impute the full scale value. You've got 7 different items on this scale, 2 or 3, and 1 or 2 items might be missing for each person. So you want to impute the individual scale items first before you do anything to create the overall scale. So here now, once I've got those individual items imputed, I want to create the actual scales. My 2 scales are BDS and EDR. BDS had to do with depression. EDR was eating disorders. So you can see how I've done this. There's more sample code there for doing this in a loop. That loop is saying, okay, for the imputations, for all of the imputed data sets, go through and create this variable. It does it for missing imputations 1, imputations 2, imputations 3, which is just how it's labeled within Amelia. And then the Zelig command is used for the pooling phase of imputation. In the pooling phase, that's when we put everything together and do one analysis. Basically, technically what it's doing is it's doing 20 different regression analyses. We don't really care to see all 20 of them. What we just want is those pooled, and they're basically averaged. There's a little bit of other stuff going on, but you can just think of this as the average of the different approaches. So that's doing missing data imputation with Amelia. You could also do this with the mice package. I go back and forth as to which I like. I kind of like mice better, but Amelia runs a lot faster. Just to show you, you could also do a version of this in ML. The results are going to come out a little bit differently. This would probably be the way that I would approach this if I was doing it. The reason why is that with multiple imputation approaches, you have a lot more assumptions, a lot more diagnostics. There's more stuff that can go wrong. ML approaches are maybe just a tiny bit less accurate as multiple imputation. However, they're a lot easier and they have fewer ways to go wrong. I think the general advice among people working in missing data is to use ML is that unless you're an expert in terms of multiple imputation, unless you've had training in doing multiple imputation, probably just relying on ML is your better bet. I did this in Lavon. Lavon is something that we'll see when we talk about confirmatory factor analysis. I hope to have a video up on that relatively soon. It's a package for structural equation modeling, or Lavon basically stands for latent variable models. We'll talk about what latent variables are. What I did here is I created the scales as what are called latent variables. You can just think of that for now as a composite variable comprised of each of the different items. And then I predicted EDR, eating disorders, from the 3 predictor variables, depression, abuse, and BMI. And then each of the variables here are further listed as predicting themselves. Notice that I don't have EDR or BDS down there. The reason why is that those are automatically generated by the command above. These are just the measured variables in the data set. All right, to run the model, I use the command SEM. I tell it the name of the model that I just created above, where the data is, and then the only thing we need to do to handle missing data is simply say missing equals ML. And we have everything handled automatically for us. And then I summarize it. We get a lot of information, but it's just the regression results here that we really want. One thing that you'll see is that the estimates are going to be very different. Levon uses what's called generally uses what's called a standardized estimate. Basically it is a standardized regression coefficient, whereas Zelig was using an unstandardized coefficient. So you can see there's a difference there. The z-values are a little bit different, especially for BDS. However, we see, the things that were significant in the multiply imputed data sets are significant using Levon, using maximum likelihood imputation as well. So it doesn't make any difference there. This is probably a little bit more divergent than other approaches, and the reason why is because we're using a slightly different estimation approach, but I think the big message is they're both going to tell you roughly the same thing about your data. You're going to have significance in some places, not significance in others, and you won't see big differences in the different techniques. All right, you also get a lot of extra output, intercepts, variances here. Doesn't really matter very much. All right, the last problem examine statistical power. You can see on my hat, 1 minus beta, statistical power. I asked you to predict doctor's visits from physical health, mental health, and stressful life events, as we did in the in lab number 3, and to use those correlations as a guide for doing a power analysis with a goal of having power of 0.8 for the R-square model and for 2 of the coefficients, stress and physical health. The reason why I only said 2 of those coefficients is because mental health wasn't significant in the first place, and it had a very, very, very tiny coefficient, so you would have to have a sample of nearly millions to get power for mental health. You can see I've pulled the different correlations. The notation here for the power to the people package is RY1, RY2, RY3. That's the correlations between the dependent variable and each of the predictors. So you can see 0.44, 0.26, and 0.29 goes in the code. And then the correlations between 1 and 2, 1 and 3, 2 and 3, those are correlations based on those are correlations that are based on the relationships between the predictor variables. So you can see 0.5, 0.31, 0.37, and then I started with N of 47. I just kind of arbitrarily started there. N of 47 gives us power for the R square around 0.8. However, it doesn't give us adequate power on any of the individual coefficients. So what I did is I ramped up the sample size until I found where I hit 0.8 on at least 2 of those coefficients. You can see with B2, it's still very, very, very low. Again, that's why I asked you just to do it for the first 2 coefficients, or for the first and the third. All right. If you're interested in just getting a bunch of different analyses so you can find where to land, I put here an example of doing this within a loop. I said for n in sequence of 200, 300, 10. What that says is start at 200, go all the way up to 300 by increments of 10, and it just plugs that into the sample size statement, and so we get 200, 210, 220, 230, 240, and so on. A nice way to kind of figure out pretty quickly where you're going to need to be in terms of your power analysis before drilling down and getting a more exact number. So we can see at 260 we're at power of 0.79. 270 power at 0.813 for the third coefficient. So what that's telling us is it's going to be somewhere in between, and where we ended up was 261. That's when we hit power of 0.8. So those loops, if you want to play with them, they can be time savers using this code as well. All right, that's about all I wanted to go over here. Again, I will continue to do the lab reviews so that we can talk more about the code behind some of the analyses, as that's code that you'll be using for homework assignments, for the various homework assignments. So hopefully that will help you to get a little bit more context in terms of what we're doing. All right, I will stop here.